episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show with another fascinating guest who is helping to create a better tomorrow for all of us. Today, we have the honor of being joined by Dr. Julie Marble, who is a senior scientist at the Johns Hopkins University Applied Physics Laboratory, leading their research there in human autonomy, interaction, collaboration, and trust. Dr. Marble earned her PhD in human factors and cognitive psychology from Purdue University. And after she graduated, she joined the Idaho National Laboratory, which is one of the national laboratories of the United States Department of Energy involved in nuclear research. First there in the Human Factors Group and then in the Human Robotic Systems Group. Following INL, she joined the Sentient Corporation, where CEO, she led a DARPA broad agency announcement on Neuro-Technology for Intelligence Analysts. She also led research to develop intelligent decision aids for the maintenance of Navy helicopters. After that, Dr. Marble worked as a senior scientist with the U.S. Nuclear Regulatory Commission, leading international and U.S. studies on human reliability analysis in this extremely vital domain. And related to this, she's internationally recognized for her work and is co-author of the SPAR-H method, which stands for Standardized Plant Analysis Risk Human Reliability Analysis, which is the most commonly used method of human reliability analysis in the United States. She's also a co-developer of Cultural Effective Model, which integrates cultural impacts into human reliability in order to predict operator behaviors. Dr. Marble then joined the Office of Naval Research as a program officer. There she established the Hybrid Human Systems and Human Factors of Cybersecurity programs. She was then appointed to the NATO Collaborative Science Office, the Science and Technology Office, Human Factors and Medicine Research Task Group on Human Factors and Cybersecurity in 2014, and she joined Johns Hopkins in 2015. Dr. Julie Marble, thanks for taking the time to come on the show today.
Thanks for having me.
It's a real pleasure. I'd love, as we typically do, to hand you the floor for a couple of minutes, just if you could take a little time to introduce yourself. You could take us back a little bit to sort of the early days and basically where you grew up, how you got interested in STEM and engineering, and basically this fascinating field of human factors. I think that'd be a great way to start everything off.
Yeah, so I grew up in Burlington, Vermont, which is a tiny little city. I went to the University of Vermont, and I have to say that I got into human factors absolutely through a sideways route. I was, like a lot of people, I floated around from major to major, not quite finding what I wanted to do. And I had finally settled on biology with a psychology minor. And I was basically proving to myself in the labs that I really shouldn't be a biology major, because every single biology experiment in a lab that I had somehow went horribly wrong. The research assistant killed off my fruit flies in a freak accident. I had a botany class where the professor swore up and down that cherry tomatoes always have 4 compartments. Mine had 5. We were dissecting plants, and we were supposed to, in this one part of the plant, there was either supposed to be nothing because it was a distraction from the parasite, and we opened up mine, and instead of having nothing or the parasite, I had the parasite to the parasite. So, things were kind of coming together and saying that maybe I shouldn't be a biology major, but I was having a blast in psychology. At the same time, I was dating someone and who I later married, and he had decided to put an entry into the Tour de Sol, which was a solar car race from Boston to Burlington. And so, of course, I joined the team. And it got really kind of funny because I was the smallest and lightest member of the team. I'm almost 6 feet tall, so funny. But along the way, we're designing this car and we're designing it around me. And I ended up having a lot of disagreements with the other engineers, because the one that I remember was that one of the engineers wanted to save about 75 pounds by having a handbrake for this car that could do 60 miles an hour. but I don't have the upper body strength of a gorilla required to stop a car at 60 miles an hour with a handbrake and all. So we'd have a lot of discussions like that. We ended up entering the race. We did pretty well. I think we got 5th overall, which is, you know, I think there was 6 in the category, but still 5th. At that point in time, you know, I was finishing up my senior year of college, and I was looking around and trying to decide, well, what is it that I want to do? And I found this program called Human Factors, which is designing things, designing machines, designing systems for human use. And it was in the cognitive psychology program at Purdue University. I applied to Purdue. I did not get accepted initially. So I took, again, the sideways route, and I asked to work for a year in the lab of Dr. Robert Proctor, helping out with his experiments. And I also took his Human Factors intro course. And at the end of that year, I applied again, and Robert let me in, and it's been a fantastic trip since then. Continuing on with, you know, getting into everything sideways, I got into human autonomy interaction in also a very similar sideways manner. At the time, I was actually interested in human aviation incidents, but literally I was walking down the hall with the latest chapter of my master's thesis in my hands to go ask my advisor, Robert Proctor, to read it. And I met him in the hallway, and I said, I need you to read this. And he took it from me and he said, fine, I'll read this tonight, but I need you to go teach for me now. I was not his teaching assistant at that point in time. You should go teach for me. And then after that, you're going to go over into the electrical engineering department and talk to Dr. Tony Maciejewski. His student needs some help with a controls problem. And it turned out that the controls problem was for a planar, a flat arm, a flat robotic arm that had 3 joints. And the control issue was that if one of the joints froze, then how you were actually controlling, inputting the direction of where the arm should go would get completely mucked up. So you'd tell it to go left and it would go behind. You would tell it to go forward, it would go sideways. So I was working with him to come up with algorithms that could make sense to a user and they'd still be able to go forward. And so after graduate school, I finished up my PhD. I was actually between my prelims and my dissertation defense, I looked for internships, and I had run across Idaho National Lab. That internship didn't work out. They were just slow getting to me. So I took an internship elsewhere. But then after grad school, I reapplied there, and I was given my first job in the human factors group there, working with a lot of fantastic people who I am still colleagues with today. And that's where I really got into working with robotics, looking at navigation systems and trying to develop interfaces that make sense when you're trying to understand the environment that this robot is in. And literally, you know, you've got a camera on it, you've got a forward-looking infrared system, you've got a sonar, but literally it's like trying to understand the world when all you can see is what's in front of you through a paper towel tube. So a very, very small snapshot of the world. So that's how I got to where I'm doing now.
Awesome. Awesome. Really great. It's I love hearing, as you said, the sideways components of stories, but that was great. You know, in looking at the field of human factors in general, it is truly what one would call multidisciplinary, in the sense it brings in engineering, psychology, physiology, biomechanics, all sorts of different disciplines. And when I go to the Purdue site and I look at sort of the offerings and sort of all the different, I mean, it doesn't seem there's anything that human factors does not touch on nowadays, I guess, with the advent of just automation and computers and artificial intelligence, whatever, is everywhere now. Could you just talk a little bit about human factors in general, when this became a discipline, and then sort of how it's blossomed in so many different areas, industry, academia, and so forth?
Sure. So historically, human factors really got its start during World War II. They were creating more and more planes for flight, and there was the question of how to create the control system for the plane so that you wouldn't have accidents. And planes are kind of interesting because you put it's go and whoa. So you push forward to go, you pull back to whoa initially. But there was a lot of accidents just around aviation, and so they had to learn what characteristics you wanted in a pilot. So what makes a good pilot? Well, eyesight is one thing. Good spatial understanding is another. But then they also had to build the controls, and they had to build the cockpits around the pilots so that they could actually, withstand these forces on them. But then the other big critical area for human factors came up in the late 70s with nuclear power. So there was this little thing a lot of people have heard of. It's called 3 Mile Island. And 3 Mile Island is interesting from a human factors perspective because it gets you into the understanding of the human role in this very complex machine. So not to go into huge detail, but essentially what happened in 3 Mile Island was there was a release valve called a PORV, a pressure operated release valve. And steam comes out of this valve and when in this case, when the control was energized, the valve would open, okay? And so on the control display, there was an indicator of whether or not the valve was energized, which meant that the valve was open or shut. And essentially what happened was the valve got stuck open. So you had a lot of steam, and this is not like, this is not radiated steam. This is clean steam because it's the way the nuclear power plant ran is that you've got the rods in one set of water, and then there's coolant water around the thing that's containing the rods. So you had steam escaping. And so when steam evaporates, the water level goes down. So they were losing coolant. But when they looked at this PORV, it said it was closed. So the operators thought, the operators, for the most part, had been trained on US nuclear submarines. Now, submarines are nuclear. They run in very similar ways. You can kind of think of a nuclear engine as not unlike a steam engine. But one of the big differences is the size of the pipes. Okay, so on a nuclear power plant, it's possible to get something called a steam bubble, where a bubble of air boils out of the water and essentially clogs the pipe. That's possible on a pipe that is up to a certain diameter, like a couple feet. In nuclear power plants, the pipes are as wide in diameter as I am tall. Okay, so it's really hard to get a steam bubble of that size. I would actually argue impossible. But the operators coming out of US nuclear submarines had been taught that steam bubbles were possible. So they see that the PORV is shut, so they don't think that they're losing coolant. They have been trained that it's possible to block the pipes with air. And so they thought that they had a steam bubble. And so the response to that was to pour off more of the coolant. Okay, that's the correct response. That is the worst thing you can do if you're actually losing your coolant through PORV. So, and this continued on obviously for hours and hours until, as the story goes, one of the operators who had been, I believe, if I'm remembering my story correctly, he had been like about to go on vacation, so he took several more hours to get to the control room, and he walked in and he literally moved a lockout tagout tag, a tag that was placed over something to say this thing is in maintenance. they saw this other indicator that the pore was open. And because of that, he realized what was actually going on was that the pore was stuck open, they were losing steam, and collected the issues. Sorry, my other phone was buzzing, and actually stopped the event. You know, he told them what to do, he recognized the actual situation. Now, the other piece of this is that about 6 months earlier at a different nuclear reactor, a similar event had occurred, but the operators had recognized very early what was going on and stopped it. And they didn't have a way at that point in time of sharing that information. So you had sort of a perfect storm of a number of things happen in that event. You had operators who had been trained excessively for a slightly different environment. You had a bad interface. And it's actually funny, you can go and look at old nuclear power plant interface pictures. And there's one that I recall that was in one of my textbooks. And it was 3 toggle switches that did very, very different things, and they were very close together. And so the operators had taken beer taps and stuck them on the toggle switches so they could tell which toggle switch they had just by reaching, because, you know, beer taps are all different shapes.
Right.
And so they could tell without looking. So you had, so you also had that pore interface design. And then you had essentially groupthink going on. So a lot of things happened. And that really was another issue that really pushed forward the understanding that you've got to take into account the human's role in this complex system. And as systems are getting more and more complex, there's a lot of time in engineering belief mindset that, well, we can just train the operator, we can just train the user, or we're going to design the system so that that there is no human. But the human is always going to either be the receiver of the information or the requester of the information or the ultimate decider, at least for the foreseeable future. So trying to say that the human doesn't matter is incredibly short-sighted in my opinion. And now as we're getting into artificial intelligence, I start seeing all kinds of issues wrap up. Artificial intelligence is interesting for any number of reasons, but one, it's mathematical, okay? So it's going to make a decision in a different manner than a human.
Okay.
Two, if you're talking about things like reinforcement learning, where the AI is trained when it gets it right to do more things along those lines, to really simplify reinforcement learning a lot, we don't know what it's being trained on, okay? And so there's a major DARPA program that's fantastic called the Explainable AI Program, where the understanding is that if you explain to the user why the AI came up with the solution that it did, then the user is more likely to accept that answer. The problem is, what if the user still doesn't understand that answer? And we're getting to that point where we don't understand that. So what I'm arguing with my research is that we need to build systems that understand the human and can say, oh, you know, Ira has not seen this piece of information and Ira is making the wrong decision. If I provide this piece of information, then we can have a shared mental model, a shared understanding of what's going on in the world and move forward together. And so the system becomes very complementary to the person.
You know, Julie, just leveraging what you were just talking about, I'm sitting here in downtown Philadelphia, and 3 Mile Island is, you know, 5 hours that way. But I'm a child of the 60s and 70s, and I remember it very well. You know, it was between that and the Cold War. It was one of those things that had me up at night. When it comes to and I guess let's start at sort of your Nuclear Regulatory Commission work and the SPAR-H analysis that you're so well known for. Whether we're talking about 3 Mile Island, Chernobyl, Fukushima, and all these, you know, whether it's a tsunami that hits or an explosion and it's not there anymore, or whatever these, you know, these horrible problems besides someone messing with the valve, and do some of these risk analyses that really smart people like you work on ultimately apply to these other really horrible scenarios at the same time? Okay.
Oh, definitely.
So talk about that a little bit, because that's very reassuring to people like me.
Yeah. So in order for a nuclear power plant to run, it actually has to be provably safe. Okay. So they do something called probabilistic risk assessment, where they create the curves and the probabilities of every component and system in the nuclear power plant and say, this is the probability of failure in this type of an event. And the probability of failure has to be incredibly low, okay? So we're talking about the probability of an event at less than, I think it's, well, I don't want to give a number because I can't remember the exact number, but it's less than 1 in 100,000 events, okay? So it's a very small number. And part of that probabilistic risk assessment includes the prediction of the human probability for error in that event. And that number also has to be very, very small. And so you have one conditional probability and another conditional probability, and you mathematically combine them, and that total number has to be very, 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 very small.
That's small.
In Chernobyl, a lot of things happened that can be traced back to human events. One of the things that stands out to me was that, so initially they were going to be doing testing of their system. They were going to be powering up the system and bringing it back down and powering it back up and bringing it back down to fully understand the physics of this reactor, because this reactor was developed to work a little bit differently than a lot of the reactors in the US. I don't remember what the coolant was, but I don't believe it was water. Anyhow, the tests that they were going to do, they had a crew that had been very, very, very highly trained. But then because of the amount of time that you can be on shift, they weren't actually able to start the tests with that crew. So they were going to go with the backup crew. And if I remember correctly, they also weren't able to start with the secondary crew, who had also been trained quite a bit. They had to go with the tertiary crew. And don't quote me on that. It might have still been the secondary crew.
That's okay. I've only watched the HBO specials on. Sounds good.
Yeah. Okay. So anyhow, so this crew was not as well versed in the test. And they're bringing the power up, they're bringing the power down, they're bringing the power up, they're bringing the power down. And as I had it explained to me by a nuclear power plant operator many, many years ago, essentially they outflew the physics of the system. They brought it up too high and kept it there too long and didn't recognize the problem. So again, a lot of human issues. I mean, there's organizational issues right there with why did they go with the tertiary team? Why was the tertiary team not as well trained as the first two teams? Why were they bringing the system up and down that high in the first place? There's a lot of questions that go on there. Fukushima is also similar in that there was a tidal wall around the area that was supposed to be high enough to withstand a once-in-a-century tidal wave. It was once in a millennium tidal wave. So they had some science, some geology that said that they could have a tidal wave of that size. But they thought that that building this lower wall, which would take care of the majority of waves of the size that you would see once in a century, would be high enough. So, I mean, again, that's not within the nuclear power plant itself. That's within, you know, the civil organization, but still, it needs to be considered. So that gets into human factors, and you see this through a lot of well, unfortunately, catastrophic accidents. And I have unfortunately gotten some weird looks on airplanes when I'm reading about airplane accidents as I'm
Have a different seat, please.
yeah, I've had that. So, but anyhow, it's absolutely fascinating. And if you'd like to talk with other people who are more versed in that, I can definitely give you some names.
Great,
So.
great. Before we get to your the sweet spot of human-robot interaction, I just wanted to, one other place I wanted to stop was Office of Naval Research. You were instrumental in part of cybersecurity research there, looking at various issues with human performance and then sort of vulnerabilities on the cyber front. Can you just talk about this for a few minutes? Is this sort of cyber vulnerabilities a la an Ed Snowden that steals something and leaves, or is this how somebody like me working at a top secret location and some, I don't know, North Korea sends a cyber attack, how I deal with it? And take us through that little journey if you would.
Sure. So I'm more interested in you at the computer dealing with a cyber attack.
Okay.
The other part that you're talking about falls more into other folks' areas of interest. Social influence being one of those areas. But really, what I was interested in is the human role in that cyber attack. So there are all kinds of cyber best practices. You're told to, use a variety of passwords. Should you write them down? Should you not write them down? Should you use a password keeper? Should you not use a password keeper? How do you recognize that your system is actually under attack? And if you do manage to recognize that it's under attack, what do you do about it? Why is it that people make choices that can open up their system to vulnerability? So it ends up being very, very complex, but there's a lot of just human performance issues. And one of the things that we see very often is that you have all of these cyber hygiene procedures that you're supposed to use in order to keep your system safe.
Okay.
Get in the way of you doing your job. And so what do? You find a workaround. And that workaround can open up a vulnerability. I'm not supposed to use this particular piece of software because it's got a known vulnerability, but darn it, it's the thing that really gets, is really able to solve the problem that I'm trying to solve. I'm not supposed to click on links that I don't know within the internet, but this link right here looks like exactly the information that I need. And so what's gonna hurt if I go into the paywall and put in my credit card? Well, it's not a real site. We all get, oh man, the amount of ridiculous spam that I get. We've all gotten those email where it says, oh my God, your Amazon account has been, and you need to log in and collect. How many people listening to this podcast have actually fallen for that? And I'll give you a tip. If you click on the sender link and put it in and then paste it into Notepad, if you're looking at it on your phone, you can then see that it's not actually coming from Amazon. It's coming from return to Joe at Korea or something like that. So, so what I'm interested in is what causes the person to make those fatal errors that open up the entire system. And then the other half of that is cyber operators. Wow, you talk about a job where you're drinking from a fire hose. They have so much information coming at them so quickly. And one of the issues is we don't necessarily know how they know what they're doing. They know what they're doing, okay? They're very, very good at what they're doing when they're trying to figure out if something's an attack, if something is malware, but they all have different ways of doing it. So how do you build tools to help these experts when they all do their jobs slightly differently? So that's another area that I'm interested in, is what visualization tools do they need? What information do they need to look at in order to determine if something is an attack versus something that's safe? How do they make their decisions? How do you enable them to make their decisions very, very quickly? So those are all things that I'm very interested in. Can we come up with aids to those decisions? Things like that.
Really cool. Really cool. All right, getting now down to humans and robots, which I know is a very hot area for you. We've touched on different areas of robotics lately. I spent some time with Hiroshi Ishiguro over at Osaka University, who's building these androids that are sort of indistinguishable from humans. I recently did a show with Mihaela Chita-Tegmark up at Tufts, and on how in Parkinson's patients that can't move their face, that robots can start to infer things from speech. Zheng Zhao at DARPA was on talking about intelligent AI, or AI that's a better research partner. Take us on a little journey, if you would, between into the area of human factors and robots, and some of the issues that you're most interested in, and I guess some of the things that concern you, because obviously you're looking for that 1 in a trillion event, so the robot doesn't kill me or whatever. But talk a little about this, if you would.
Yeah, ironically, the past couple of years, I have chaired a session at a conference, at an IEEE conference called Avoiding Skynet: How to Build Autonomous Systems We Can Trust. But that's exactly what I'm interested in. I'm interested in trust. And I mean, the running horrible joke that I've been using is that, just like pornography, you know it when you see it, trust, you know it when you see it. First, you have to start off by defining, what do we mean by trust? And I don't mean reliability, and I don't mean capability. I'm defining trust, and this is based off of work by 2 incredible researchers named Lee and C, 2007, and then another bit of work by Colquitt, Scott, and Lapine, 2011. But basically, combining how they're thinking about trust, I am arguing that trust is a socio-emotional construct that explains why a person is willing to make themselves vulnerable to unpredictable actions by another entity. So there's a couple of key things in there. It's social, it's emotional. You, the truster, have to be vulnerable to the trusted, and you can't fully predict what the other entity is going to do. Those are key things.
Okay.
That doesn't necessarily mean that the other entity is fully reliable. Doesn't even mean that the other entity is fully capable. And I jokingly say that, we all have teenagers who we trust very much, and they are neither, fully capable or fully reliable, but we do trust them. So how do you build an autonomous system that a human can trust? So especially now, as we're getting more and more autonomous cars, and we have lane departure systems, and everybody's hearing these horror stories about the lane departure system mistook the line that it's supposed to be following from the crack in the road and almost pulled me into the other lane, or the FLIR system, there's issues with FLIR and rain and everything like that. They are flawed. So you have to understand what the limits are on this system, but you also have to understand, and this is what I was referring to earlier with AI, you also have to understand how the machine is making its decision, and it has to understand how you are making your decisions. So part of what I'm interested in, and you probably heard about this with Zhang Zhao, is computational is a mammal to infer what another animal or human is thinking. So if you and I were playing basketball, I could look at you and just with a short move of my head indicate where where I was going to pass the ball to you, so you could move into that position. We see this in all kinds of animals. Ravens, if they know they are being watched, will fake hiding food to fake out others. It's an important part of deception. In order to lie to another person, you have to know what that other person could know. And that's theory of mind. It's an integral part of teaming and collaboration, because you have to be able to anticipate when the other person is going to make mistakes. And so one of the things I'm interested in is, how do we build that within an artificial intelligence? How do I give an artificial intelligence insight into my decision-making? Because human decision-making is really flawed, okay? We make all kinds of decisions that are fast and they feel really good, and sometimes they're just horribly wrong. And a lot of people have read Daniel Kahneman's book, Thinking Fast and Slow, and that's what we're talking about. So you've got these beliefs that they're fast, they feel like they're right, but when you go and plug and chug through them, they turn out to be wrong. So how do we enable a machine to anticipate that and to complement that? And also the other half of that is, how do I, as a human who has, limited amounts of information I can process, limited time, limited computational resources, how do I know if the answer the machine has come to is the correct answer or not? So that's what I'm interested in. My most recent research has looked at two aspects of that. The first one was research called Escape with Partner, which is an acronym, which is the experimental suite of collaboratively achieved puzzle exercises with the platform assessing relationships and trust with non-economic risk. I did not with that acronym.
That's a tough acronym, yeah.
But what we were looking at, we built a VR, a virtual reality game, where you and a teammate teamed up to essentially escape the room. And in the room, there are boxes and laser guns and tractor beams and things that you can use to get yourself to a door so that you and your teammate can escape. Now, because I'm a cognitive psychologist, I use deception a fair amount. And some of the people were teamed up with humans, and some of the people were teamed up with robots. And we didn't necessarily let them know accurately who they were teamed up with. So they did 4 of these puzzles where they had to go through. And the first puzzle, they get through that with their teammate. And then we say, great, now you're gonna do the second puzzle. The second puzzle they get through, and we tell them at the end of that, okay, now you've played with both the human and the robot, you're gonna do 2 more puzzles. Who do you want to play with? And they told us, and they did 2 more slightly harder puzzles, okay? And at the end of that, we said, hey, great, congratulations, you're in first place. If we only want to have 1 winner of this whole tournament, if you're still tied for first place, will you come back and do 1 more round? And they all said yes, because it was a lot of fun to do. And then we said, okay, well, who do you want to play with in that round? Do you want to play with the human or the bot? And they gave us their answer. Now, the critical things to know is that in that first round, the first time we asked them who they wanted to play with, about half said, we want to play with a human, and half said they want to play with a bot. Mm. Going into the third puzzle, we saw a slight shift. About 70% of people said they wanted to play with the human, and 30% said they wanted to play with a bot. In that final, here's all the money question, about 90% of people said they wanted to play with a human, and 10% said they wanted to play with a bot. Now, here's where it gets interesting. We asked them a bunch of other questions, too. We asked them, which of the puzzles did you do with a human, and which did you do with a bot? And they did not know. They all did 2 puzzles, one of the first 2 puzzles with a human and one of the second 2 puzzles with a human. They were all over the board. We had some people said that they did all of the puzzles with a bot. We had some people say that they did all of the puzzles with a human. We had people say that they did the first 2 puzzles with a bot and the second 2 puzzles with, we had every combination that you can come up with in that situation. So they really didn't know who they were playing with. The other part that's interesting is we also asked them, okay, which puzzles do you think you did the best at? Which puzzles did you get out of fastest? And which puzzles did you and your avatar die the fewest times in? And what was interesting was that they responded that the puzzles that they thought they did the best on were also the puzzles that they thought they had played with a bot. And then they said at the end that, no, we want to play with a human. So who they selected for that final trust exercise was not who they thought they did the best or the best with. And so it's really an interesting finding. And we're still following up on that, but it's absolutely fascinating. The other bit of research that I've been doing lately is around one of the AI grand challenges that's put out, they're identified by Facebook, DeepMind, Google Brain as the next big issue for AI.
Okay.
A few years ago, those groups identified a very simple card game called Hanabi as the next grand challenge. Hanabi is an interesting game. Unlike poker or bridge or Go Fish or anything like that, it's not a zero-sum game. It's a collaborative game. So it's not a case of I win, you lose. We either win or we, the whole team, lose together. And it's deceptively simple. The goal of the game is to build 5 piles of cards according to color from the number 1 to the number 5. Okay, really, that's your goal. But in the deck, there are more 1s than there are 2s, there are more 2s than there are 3s, there are more 3s than there are 4, and there's only 1 5 of each color. And your final score is the value of the top cards on all the puzzles. So
Okay.
the game is 25 points. And there's one other hitch, or actually 2 other hitches. One, you can't see your cards. You can see all the cards of everybody else that you're playing with, but you can't see your own.
Okay.
And communication is extremely limited. So on your turn, you can play a card onto the decks that are in play. You can discard a card, or you can give one of your teammates a hint. And that hint is very, very formulaic. You can tell one of your teammates all of the cards in their hand that are of a particular color, or all of the cards in their hand that are of a particular number. And you can't do it with any kind of emphasis. You can't say, this is a 1, and this is a 1, and this is a 1. Say, these are your 1s, or these are your blue cards. And it gets interesting, because when you're playing with other people, one of the things that you'll do as you get good at this game is, let's say that there's 4 of us playing. I might not tell you something about your cards. By not telling you something about your cards, I've told you something about your cards. I might be telling you just simply that you have no cards that you can play.
Right.
Or I might give the person next to you a hint, and you can see the hint that I've given that other person. And from that, you might infer, oh, by the time it gets to be that third person's play, that card will be playable. Therefore, something in my hand is playable. What in my hand is playable? That's theory of mind, which we talked about earlier. So a lot of researchers have built AI that can play this game. And they can play it really, 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 really well. So if a perfect game is 25 points, there are agents out there that average 24 points per game, which is really good. You can go to a website called Hanabi Live and download some statistics. People don't play quite that well. We're good, and experts are very, very good, but we don't average that kind of level. But here's the thing about the AI. Those AI that are averaging those kinds of scores, they're only getting those scores when they play with instances of their own self. Okay, so that's called self-play. You take an agent that's been taught a certain way. Let's call it Rainbow, and it plays with an exact duplicate of itself. Okay, you'll get very high scores.
Sure.
What we showed last year was we took those agents, we trained them up. We trained up a set of agents that had been built outside of Johns Hopkins Applied Physics Lab. And we trained them up. We replicated what we'd seen in the literature about their performance. But then we said, okay, how do these 3 agents play with each other? And they did really poorly. So instead of averaging 24 points per game, they were averaging 5 and 6 points a game. And then we said, okay, well, let's see how they do with people. Okay, and I should add that these are just two-person games. I was not doing like 5 entity games. So then we had people play with them. We got something like 70 games, and those games were just as bad. And it's interesting because one of the agents that we used is called a hand-coded agent. It was designed to replicate rules that were derived from human strategy. And that one also didn't do very, very well at all. These games are still down around 6, 7, 8 points. So the question then becomes, what do you need to do in order to give an agent an understanding of the human so it can infer what the human is doing? And more importantly, how can you take that application and go beyond just a silly card game, which is fun, but I mean, the outcome of a card game does not, impact the safety of the world.
Right.
So what we're about to actually launch here at APL is I'm running an internal challenge where I'm challenging my really, really smart coworkers to build bots that can not only play really well with other bots, but which then also play really, really well with humans. And I don't have an answer right now for how they're going to do it, but I'm interested in seeing what they do and how they do it. I have my own pet theory of how to do it, but I haven't had a chance. I'm actually shopping around trying to see if somebody like Zhen Zhao at DARPA will fund it. So we'll see what happens with that.
Really cool stuff. Julie, we get contacted a lot when I do these shows by our younger listeners that are starting out, maybe graduating high school or freshman year of college, and not exactly sure what they're doing yet. They may listen to the show and they're like, "Wow, I want to do what Julie Marble does. I want to be Julie Marble. This is just, you're such on the bleeding edge of things and these concepts that, over many of our heads." Any advice in terms of, obviously you talked about sort of the sideways trip that you took, but any advice for these folks, what they should focus on specifically early on, a broader range of disciplines, any specific things to at least get them more excited about human factors, and if they're really hot on it, I focus on X, Y, and Z as opposed to this other stuff.
Yeah, so I would, a number of things. One, it's almost unfair to ask a high school kid, what do you want to do for the rest of your life?
Sure.
I'm incredibly lucky because while I stay in the same field, I'm doing something different every couple of months. And I have to learn a new area every couple of months, which is absolutely fascinating to me. But the other part too is don't be afraid of that. Okay, don't be afraid that you don't know what you want to do. So try a lot of things. And there are a lot of actual internships out there for high school students and college students. And I'll give a blatant plug. Johns Hopkins has 2 of the best internship programs for high school students and college students that I've seen. I have had 2 high school aged interns in the past 2 years. One helped me with developing the VR program that I mentioned, partner, and the other one has helped me with the Learning to Read Minds challenge around Hanabi. So they're fantastic opportunities to learn. I myself have not had a college intern yet, but that is probably going to change this year. I'm thinking about doing that this year. But they're just fantastic opportunities. So look for internships, and let's say you live in Burlington, Vermont, where there is not large industry. That doesn't mean that you can't find an internship. Look around at what is around you, and go talk to folks, because I would dare to say that the majority of scientists, if they had a high school student come up to them and say, I want to do an internship with you, or I want to learn what you do, they're going to figure out a way to make that happen, okay? Because that's part of what science is teaching, okay? It's learning how to think about the world, testing hypotheses, but yeah, I mean, they're going to find a way to get you experience if you've demonstrated, that much passion. So yeah, just because you live in the middle of nowhere, Williston, Vermont, it's not gonna stop you. And email, read stuff. and email people. You never know who is going to answer your questions. So I always like Neil deGrasse Tyson's story about how he got into physics, and just you know, and just getting out there and actually meeting with his, you know, his hero. And if you haven't read that story, go read it and find out who I'm talking about. So yeah, email them. You know, if I got an email from, you know, a college student who said, "Hey, I'm interested in this," I'm gonna reply. It might take me a week, but I'm gonna reply. The other part too is look around at the problems and the things that you're worried about, and think about what goes into the solutions for that. So human factors is interesting. So my degree program was in the cognitive psychology department, but I took classes in industrial engineering. I took classes in computer science. I took classes in kinesiology and ergonomics. So it's not just one thing. So, you know, no learning is ever wasted. So look around and think about the things that are interesting to you, and leverage those things. And sometimes you're going to have to suck it up and take that horrible class that you really don't want to take, that is nothing but, you know, pure math or whatever, or whatever it is that, you know, it's nothing but writing, but that will help you. That's the other part too. Emphasize math. You don't have to be a mathematician, but it is incredibly helpful to be able to read an equation and get a general idea of what is going on in that model. It is its own language. And you also have to be able to write. Mm-hmm. And one of the best ways to learn how to write is to write. Public speaking. Most people are terrified of public speaking. You get better at it the more you do it. Yep. So take a drama class, take a stand-up comedy class, you know, learn how to deal with the fact that you're standing in front of 50, 75, 100 people, and it doesn't bother you anymore. So those are the things that I would recommend. And the other part of that too is those classes, drama, debate, those classes that often get poo-pooed, those are the things that are going to make you impressive during an interview. You can explain what you're thinking and explain your passion. It inspires other people, and it makes them want to help you. So yeah, I mean, you know, in high school, I was a drama weed. Okay. I was in drama, I was in chorus, I was in debate, I was on the trivia team. I was the quintessential nerd. And you know, those things help me, because I can talk to a lot of people about a lot of different things. So yeah, and ask questions. Never be afraid to ask questions, because it's not a stupid question. Even if you preface it with, "This might be the stupidest question this week," still not a stupid question. And I do that frequently. Like, "I really don't get this. I'm a total noob in this area. Explain this to me like I'm in third grade." And it goes forward. So those are the things that I would recommend.
Wonderful, wonderful. Julie, one final question. Obviously, you've had an amazing career in academia, in government, in private industry. You've met, no doubt, hundreds of equally fascinating people along your journey. Take some time, if you would, just to mention, shout out to important mentors, influencers that were extremely influential in keeping Dr. Julie Marble on this path. And if it wasn't for these people, Dr. Julie Marble would be practicing law or selling real estate or doing something totally different.
Let's see, let me think about that for a sec. So yeah, people who stand out to me, Harold Blackman, Bruce Halbert, and Dave Gertman, who and Jerry Harbour especially. They were my first mentors when I was at the Idaho National Lab. Mm-hmm. In fact, I got my job at Idaho. I was at a conference. I came around a corner in a poster session I had just presented. So fortunately, I was wearing my suit, my one and only suit, because I was in grad school. And Harold Blackman was standing by a poster for work at the Idaho National Lab, and I stepped back, took a deep breath, swore several times under my breath, and then went up to him and said, "Hi, I'm Julie Marble. I want to work for you." And got into a fantastic discussion with him. And I ended up working with him for several years, and he's still a fantastic mentor. Dave Gertman taught me everything I know about human reliability analysis. And Jerry Harbour was the first manager I ever had who truly believed in me. I mean, he gave me as much rope as I possibly could and waited to see what would happen with it. And instead of hanging myself, I made a lot of macrame. Again, David Brummer, Doug Few, who I worked with at Idaho National Lab. When I first started at Idaho, David was he was building navigation algorithms for robots. And he was controlling the robot on a text-based interface that ran on a PDA. And this was so beyond horrible. I couldn't even begin to explain. And so David and I had a lot of discussions about how to build this interface so that somebody besides him could understand it. And I really love David because he is a dreamer. He's somebody who is able to convey just huge vision, very, very quickly. So definitely David is one of them. Who else would I call out? I've had a lot of other mentors. Again, I have to pull out like Susan Cooper and Arasmia Lois at the Nuclear Regulatory Commission, they were just really good examples of women who had succeeded, women who were just making a name, and especially Arasmia, who always took the time to explain everything that we were doing and why it was frankly important. And those are the big ones. Call out my friend Missy Cummings, who's a professor down at Duke University, just because it was fantastic to meet another woman who is frankly as outspoken as I am and not shy about her opinions. A lot of women they're taught not to speak up. Speak up, okay? You have a voice, you have an opinion, it is just as valuable as anyone else's. And so Missy is a fantastic person. I recommend you talk with her. She's one of the first female fighter pilots for the US Navy, and she runs the Humans and Autonomy lab down at Duke. She's a fantastic friend. I can't speak highly enough about her. It was always fun at ONR walking into a room for a review together and seeing the speaker pale. It's like, no, I've got both of them. Also Rebecca Goolsbee, who is still a program officer at the Office of Naval Research, and Jeff Morrison. So when I was at ONR, Jeff had started about a year before me, and just was very good at explaining, he was constantly updating his vision slides. And that was a useful thing for me to see, because a lot of times what is going on in my head is going on in my head. So conveying it out and pushing it out. Rebecca, she has so many projects and so many things that she's working on at one time, but there's always one connected thread through the whole thing. And she's very good at explaining that one connected thread. So those are the people who truly stand out to me. And I'm very lucky to have worked with all of them over the years.
Outstanding. And thank you for sharing that. Julie, it's been fascinating listening to your journey, and amazing the portfolio that you have in front of you, and wishing you the best with it moving forward. For everybody that's going to be listening to this episode on the podcast or watching on the YouTube channel, you've been listening to Dr. Julie Marble, senior scientist, Johns Hopkins University Applied Physics Laboratory, leading their research in human autonomy, interaction, collaboration, and trust. Julie, thank you for taking the time out of your schedule to come talk to us and tell your story. Thank you for keeping the nuclear power plant safe and the airplanes in the sky, and preventing Skynet from happening. And as we say, thank you for helping to create a better tomorrow via everything you're doing. It's been really very inspiring.
Thank you very much. This was fun. I appreciate the time. I appreciate the opportunity.
Absolutely.